The same thing, same setup.
Okay, let's get started. It's my pleasure to introduce Kristen Grauman, Kristen is one of those people who needs no introduction. She's renowned for her work in computer vision and video. One thing you might not know, I'll tell you, is that Kristen and I went to grad school together at MIT, and we used to play basketball with her future husband. And Kristen is also the last person I ever played basketball with.
Yeah.
Can't play anymore. But thank you I don't think you've ever given an IFML seminar,
No.
so it's great to have you here, and it's great to have you give a seminar.
Awesome.
Thanks for coming.
Yes. Thanks, Adam, and thanks for that painful reminder about playing basketball when you had your injury. I'm so sorry. How to go from there? Yeah. Well, thanks all of you for being here. I'm excited to tell you about our work. My theme today is about skill learning from video. So we're going to be talking about human skill. And we'll also think about how to turn that into some robot skill as well. But when we think about human skill, what do we mean? This can refer to any level really of skilled activity we have, from things like you might say are kind of lofty, things we aspire to, like sports. We want to play a sport well. We admire how someone passes the ball. We hear music that really moves us. It takes some intricate skill with the hands and the instrument, but also kind of what I would call everyday things, about things that just need to get done, like repairing a bike or cooking. These are all, just a sample of avenues where human skill is really on display. And there's a lot that video understanding of that human skill could enable. And in particular, there's two big fronts that we are looking at in our work to inspire why we want to have video understanding of human skill. One is in robotics, where we imagine, the robots that learn not purely from expensive physical experience of their own, but actually learn from watching others, us, do things in the real world. And so there's great possibility for video-based, some people will call, passive learning from video, for robots to start to operate more and more in human environments and with human-centric objects. And then the other big front that's so exciting to me is in augmented reality and mixed reality, where you can think about the smart glasses of the future that you'll put on and will be your daily life assistant with AI that can give you advice, information, tips, just in the moment you need them based on your physical context. And so in this example, yes, in learning a new skill where you want the information about how to try something new based on how you're trying to execute it right now. So these are big, let's say, application areas or need areas for human skill understanding in video. And to go a bit further on this second one, I want to show you this kind of vision video of what this could look like in the smart glasses realm. So in a mixed reality, augmented reality setting, where right now, I think, if you imagine how you learn a new skill, you may very well use a how-to video and or maybe a book, and you're going back and forth to such a resource as you try to execute this new skill. So for example, say you're trying to cook something new. But with a heads-up display, with your hands free, you could instead be operating in the world and getting the advice you need from that video or any other video right when you need it. So for example, summarizing the step that you should be doing right now, or giving you feedback about when it looks done or not based on your actions and what it can see. So of course, this assistant is seeing the world through your eyes. And in another domain or second domain, imagine in sports or other physical activities where we want to get better. And part of it is seeing how other people do it. But a big part of it for real meaningful coaching is getting feedback exactly on how we're doing it. And so you can imagine in this same kind of smart glasses setting where novel 3D visualizations would allow you to see your own swing, see it in a 3D way, compare it to that of the expert you're trying to emulate, and similarly get language-based feedback about what you need to adjust, as well as visual, physical kind of feedback about how things should look. So that's a picture of the future. And what's exciting is we can enable this, but it requires some very fundamental computer vision and machine learning things to advance. And so I'm going to focus this talk in the remainder about three of those things. The first one is fine-grained 4D grounded activity. So we're going to have to start thinking about human action in a long-term setting, in a physical setting that's no longer just glimpses of 2D things over time, but really grounded in the physical 4D world. So that'll be our first topic. I'll spend a good amount of the examples looking at that. And then I'm going to turn to this challenge of cross-view representations. So if you think about a student and a learner, often we're observing from two very different viewpoints. They're called egocentric and exocentric. And so we need to be able to connect how things look from our own view or our robot's own view to the view that we see when we watch an expert do something. And then finally, at the very end, I'm going to show you how we're starting to deploy some of these ideas and new methods into actual systems, even smart glasses systems that can provide real-time feedback on things like I was just illustrating.
Kristen, quick question.
Yes.
I mean, since you have the example of music up there, and I know that you are an excellent pianist. I mean, one of the things that seems like extremely difficult to learn from video is like watching a piano play,
Yeah.
and then thinking that you've learned anything at all. Do you really feel that, you know, in the future, like you'll be able to actually learn piano from watching videos, or is that something that you feel like just somehow,
Yeah.
you know, I mean, since you have
Yeah.
experience with it.
Yeah, I think there's an element of video that a role that video can play. And you're right, like these domains certainly have their differences.
Like cooking, I get.
Yes, yes. Yeah. Well, right. So we're thinking about the fine grain of the hands. I think when I think about piano specifically, the thing that video would stop short of, at least today, and let's talk to George about things that keep advancing, but the notion of haptics and touch and feedback there is something that'd be hard to communicate through video mining. But yeah, I think there's a role to play. And you can also think about differences in teaching when you're talking about a beginner learning or an expert learning more. On any instrument, right, where the kind of input and feedback you need is going to be different too. Yeah. So in short, I'd say it's not everything, but yes, I think there's a role that could play. Good, so let's talk about fine-grained 4D activity. And along with those technical challenges I just reviewed, of course, there are data needs to enable these kind of things. And so some of our work recently with a team of researchers at these 15 different institutions was to introduce a data set and a benchmark called EgoExo4D. This we released last year, and it's exactly focused on human skilled activity. So it's a data set, more than 700 participants took part in, where they have a variety of skill levels, and they perform skilled activities like you see here, includes music, dance, healthcare. They were teaching CPR, basketball, soccer, bouldering, and others. And so these 700 plus people doing these things in more than 100 different real authentic environments. So this is out of the lab in the real world. And you'll notice we are capturing them both from the egocentric perspective, meaning a wearable camera, as well as multiple exocentric cameras, meaning stationary cameras in the same scene. And what's important to note about that kind of dual set of views is what you get. So on the ego view, you're seeing a lot about the detail of hand object manipulations, up close about their interactions with the environment. Whereas in that exo view, you're seeing, well, their full body and the pose over time, as well as greater scene context. So certainly complementary pieces of information as we want to try and understand human skill. So we captured this at scale in these many different locations. And then I can give you an illustration here. So if you had 4 exo cameras, say in this setting, simultaneously you're capturing from glasses that the subject is wearing. And we're using this research platform called ARIA. It actually has a variety of sensors on it. In addition to the multiple cameras, it also has gaze cameras looking at the eyeballs, so you can see where the person's looking over time, as well as multi-channel audio and a number of others. Okay, so in EgoExo4D, then now we're getting kind of rich data we didn't exactly have yet to put together this dynamic human activity from the first-person perspective. Here in the green camera that's reconstructed, there's the eye gaze in red. Alongside that 3D physical world. And that's what's reconstructed here. These are point clouds reconstructed from those multi-exo cameras. And this is where we start to be able to ground dynamic human activity in a persistent physical space.
Can I ask you a quick question, Kristen?
Yeah.
Is this all people with all of them already have the skills, or do you have some examples of people learning the skills for the first time?
Yeah, this is a variety of skill levels. So there's a range bucketed into 4 camps from beginner, early intermediate, later intermediate, and expert. Yeah, so on purpose, we wanted people who could execute really well and people who are still learning. Great, so alongside EgoExo4D, we put together benchmark tests. And this is just to drive research with the data on problems that open up with it, such as proficiency estimation, viewpoint translation, and others. And these challenges have been going on, both this effort as well as our earlier effort called EGO4D, for several years now, where people across the community are competing and making the results much better. So this is what this chart on the right is showing, kind of the percentage improvement over baselines we originally introduced as the years went on for this challenge. So it's been a great kind of focal point for improved ego video understanding. All right, but I've set up that data because I really wanted to show you, as far as modeling goes, next, our work on 4D activity prediction. So if you're not already familiar, right now, a common thing to do when you want to analyze a video is to break it up into uniformly sized chunks in time, and then represent each of those chunks with some kind of rich feature, and then aggregate the results of some understanding module over time. And so what this means is, we're pretty comfortable right now, or at least used to, thinking of video as these isolated 2D glimpses over time of the world. Never mind the fact that that camera is in a physical world, it's moving in a certain way, and so on. And so our goal is to rethink this and instead place our activity representation in a persistent 3D spatial context. And that's what this cartoon is suggesting, the fact that the person saw something here and then moved on over time. Well, it all is happening in the context of a real 3D environment. So that's where we come to this idea that we recently introduced called fiction, future interaction prediction. And in this work, what we want to be able to do is, again, have that grounded representation of the activity, and in particular, give fine-grained understanding of two things. One, where, so what are the 3D locations of the next object interactions? And the other, how is the body going to be moving or posing during those next interactions? And so if you think about, why do I want to predict what's going to happen? Well, think of any of those AR and even the robot learning cases where for latency alone, but in general for planning, you want to know in advance where things are going. And so it's observe some video and then predict where they're going to go next. So that's the anticipation or prediction goal. And so how we start to achieve this is by going through the video, looking for objects in 2D, and then because we can register this in 3D, we can back project to the point cloud and estimate now not just little frames in 2D, but 3D bounding boxes for objects. Like here, it's detected things in the kitchen, like the stove, some holder, cups, jars, and so on. Okay, so you have your objects that might afford interaction by the person in the scene. And then this will represent the where. What I just said represents the where. And then the how is, okay, what's the body going to be doing? What's its 3D body pose within that space? And so here at this point, we're just mining the unlabeled video for these object observations as well as the human body observations. And we're putting the body into world coordinates of the scene based on the egocentric camera. So what does that mean? Now you can go through all this unlabeled video, find objects, find body poses, and then mine for what we call interaction points. And this is any time where the person starts using an object in the scene. So, it's the body comes into contact or intersection with some other object. And in fact, we can reinforce it based on some language present with the data. But this just gives us from video to a bunch of moments where there is a person-object interaction. So once you have that data, we can train a prediction model. And we set up a model where we encode from the video frames, from the body poses, and the 3D observations. We can encode those as multimodal tokens in a large multimodal model to be able to decode back out to two things. First, that location, that's at the top here, where we want to know where are the object places where this person's going to interact next. And then when they get to those places, how are they going to be using their body? And that's the how, which we express as a distribution of body poses, from which we can sample to say, this is what the pose might look like coming up. Now we do this over relatively long time frames. So we might, in this example, so here from the video input on the bottom right, this is our kind of the innards of the model looking at the human body over the space. And then this is what we observe so far in the video at inference time. And now we're predicting forward in time. That's what those light pink bodies are and those voxels are, saying where we think the person's going to go next, what they're going to do there. And as you see the blue, this is the future as we start to observe it. And as those pinks disappear, this is where that future is being realized. And the model has predicted that these things were going to happen, by the way, in a kitchen that it has not seen before, a person it has not seen before, and then being able to know, okay, this is how the activity is likely to unfold. And so this is the where and how prediction at a pretty fine-grained level, and now really, again, grounding the 3D activity in the physical environment. And I'll show you a second example, same form. Here, a bike, someone's preparing a bike, And we observe these poses in the dark pink. And then after some amount of time, we're going to have to anticipate what are the next future poses. And so that's what those pink bodies are. And now the blue becomes, again, just what they're actually doing as time goes on. And I'll scoot through this. And you can,
Sorry.
yeah.
The pink says observation, the blue says prediction.
Yeah, there's dark and light pink. So the dark pink was observed, and then the light pink is predicted.
What's blue?
This one's predicted. That's future, which means like as time goes forward. So we've already predicted this guy. And then reality keeps going forward in time, and that's the blue. So you haven't observed this blue one, but you want to see it align with the light pink that you anticipated. Yeah.
And you're not using a diffusion model for this?
No, we're not. Yes.
How much proportion of the video did the hands or like both hands like appear clearly in the frame? Because I would anticipate like sometimes the human's not looking at their hands.
Yeah. Yeah, that's right. I mean, in general, that's something to be aware of for sure in ego video. GoPro-like cameras that look down are great for really getting the hands, but outward-looking cameras like the glasses form, you're right. You may not see the hands. Keep in mind, we have multiple views on this scene for getting the body. So there's multiple exos, so you would get the hands. But your comment calls to mind too, the fact that, a way to make this better is do something with the hands. So the hands are Barbie hands right now. It's just the full body pose, but not the articulation of the fingers, but which you could certainly want to add to get the more nuanced activity. Yeah. Yeah, Danny.
Does the model know like the task at hand or because if there wouldn't like future actions be dependent on the task that's being performed, or is it?
Yeah. Yeah, so like whether they're cooking or fixing a bike. That's very easily discernible from the video. And so I think we play both with training universal model to do this over whatever 8 or 10 kind of scenarios exist versus per action. I don't think there was a big difference. And then in the end, just using all the data together is fine. But even if you wanted to condition on the activity, I think that would be one of the easier parts of our prediction probably to do. Yeah.
Does the model also predict the time at which the person is going to be in a specific position?
It's not right now. The way we formulated this one is kind of observe what you observe and then predict several minutes into the future or a few minutes into the future. But you can imagine time indexing that as well. Yeah. Yes.
What is your featureization or representation? For video, you mentioned that people just have jumps and they make into vectors.
Yeah.
But you are doing clearly something, in 3D plus time.
Yeah.
So what is your featureization?
Yeah. So you have the explicit poses, the 3D body poses here encoded, I guess, in what is called the simple parameters, I guess the full body shape and pose. And you have the frames of the video. And then, to get the representation of our output space, we had that explicit object detection and intersection points in 3D space with the human body to give the target output space, which is voxelized version of the scene, where we need to assign in each voxel if they're going to be there in the next, 30 or 3 minutes, and as well as a pose distribution to sample from for each of those voxels.
And so at each point in time, your representation is by putting together several frames from the same time from your different viewpoints, right?
Yeah. So the video,
like this is not from a single, this is from several viewers looking at the same thing.
Yeah, actually it's a little bit of a hybrid because we allowed ourselves to use the exo to get the body pose and the 3D reconstruction. But as far as the video RGB, it's just the ego. Meaning at inference, you're watching the ego video stream. But you had the benefit of grounding the body from richer 3D multi-camera. And the thought is the more and more advanced monocular reconstruction gets, you could replace that with a single camera. Yeah.
So just to understand the training for this, so was the model trained on this particular room and this particular setting, or it's just like trained something else? This is completely new.
That's right. It was trained with other bike repair and other garages and things, but not this particular one. Yeah, so it's important to have that holdout of environment, at least for impressiveness, I guess, of what could be learned. And so why is it possible? Well, the model is going to be seeing things. I mean, the kitchen's maybe easier to imagine. The model's going to be seeing things like cabinets over there, sinks over there. So if you have someone doing something, well, you might expect they're going to need to lean for that one or reach for that one. And so even though it's a new environment, you can pick up on those cues. Yeah.
And so just to understand the task better, so here there's like 4 prediction for the poses. So are you only doing those 4 right, or just the entire, like it's a sequence, but in the video it's just like 4 snapshots of like 4 things that you're.
Yeah. So, right, it's a pool. So it's a pool of poses to say, so there'll be some voxels that light up to say these are going to be places. And then for those, sample from the pose distribution expected at each of them. And then, per the earlier question, it's pooled over time at this point. But you could imagine making it more specific and either doing shorter term forecasts or indexing over time at once. Yeah. Good. So let me pick up from here. And thank you for all the great questions. We evaluated this. This is the kind of territory where actually the baselines aren't really doing this task yet. So we kind of upgraded some 2D models to 3D to try and say if you did some straightforward 3D for those models, where would you get, and so on, looking at both the location and the pose predictions. And what the results tell you is that this is, promising, and we can quantify the errors that or the accuracy that we're improving. So this next piece, what I want to talk about is going from what the body's doing, which is clearly an important part of human activity, to what the objects are doing, which is also going to be an important part of our activity. So, this to some extent certainly had the objects present, but we were really thinking about how's the body moving, what's it going to do? And, in robotics as well, a lot of very popular, important tasks involve moving objects around. So whether it's opening and closing, moving this object here, for pick and place, push and rotate, and so on. Okay, so there's a lot of objects moving, but let's take it one step further. We need to know about objects that go ahead and change their physical state. So in an object state change, this is where often in an irreversible way, you have an object that's transformed from one shape, appearance, structure to another. Like you're chopping the avocado, you're dipping the apple in caramel, you're melting this, mashing the banana. So these are changes that have very big visual differences. Furthermore, they have very big impact on how well some interaction is proceeding or how far is it proceeded. And so we've been looking at cases like this, visual object state changes in video, and realizing that current models, say even proprietary VLMs that want to describe these kind of object state changes over time, are having a hard time. They do 2 things wrong. One, they won't be temporally specific. So it might look at sequence like this and talk about eggs being cooked, but not really have anything to say that's tied specifically to the time moments. Or the other thing they do, as you might guess, is hallucinate, because they may know a lot about what it means to cook eggs in a wok and say things that are smart, but again, they won't necessarily line up with these visuals. And so some of our work most recently was looking at what we call progress-aware video frame captioning, where we could caption at the frame level, and these are some outputs from the model, in a way that is very attentive to how things are evolving over time. And this is what you need to get those details. So for example, I just highlighted in blue some of those salient parts where, the eggs are still intact here, they're still in the same position in the wok. Now they're starting to cook, they're becoming more solid, now they're fully mixed, and so on. And so to do this, we had to do some training and some pseudo labeling, trying to disentangle when things are aligned specifically with the visuals versus when it's more incidental or hallucinated content, so that we could train to get this very fine-grained alignment. But this is for temporal, and what I just showed you with the object state changes also involves spatial localization. And so here, let's think about how we could represent a class of object transformations that involve spatial progression over time. And it's just like the ones we were looking at, where the progress happens, the chopping occurs, and this avocado went from whole, where it had been red, to now all of it is chopped. Or in any of these other examples, let's say, let's look at this bottom right, where you have an apple, it's red because it's actionable, it's not been worked on. Now it's green because it's been dipped in this, and now it's fully covered. Okay. Any of these things. So grating cheese, peeling apples, mashing potatoes, potatoes. then we would like to have these segment level masks that say, here are the pixels where the thing is still as it was at the start. Here are the pixels where it's been transformed. So why do you want to know this difference between actionable and transform? Well, if you're a human doing this task, it tells you where you need to work. And certainly if you're a robot doing this task, it tells you where you need to be doing some interaction in the scene and where are the parts where you've already got it covered. So we've actually, with reinforcement learning in the real world, we've trained policies that take these spatially progressing object state change masks, which we nickname Spock, and then use them as a way, both as input and as a reward for an RL policy, guide the agent directly to try to do the work where it's still needed. So what you're looking at here are some curves over time during training, where this is, high is where you've transformed the object successfully by what amount, and this is time or episodes of learning. And so we're rewarding the agent to increase the transformed area. And you get that from these segmentation masks that we're creating, where they're red where it thinks it's still actionable and they're green where it thinks it's transformed. So you want to maximize the quickness with which you turn everything green. And we're comparing that to a state-of-the-art baseline that has more of a language-based expression of the goal state that you line up against, as well as a simple sparse rewarding success of full coverage. And so we really could get much faster learning, an hour and a half, 3 hours in the real world for training on a variety of objects we'll see in a moment. And the other thing to emphasize about this formulation is that it's embodiment agnostic, right? That's what I really like about object state changes. It's a way to express goals that don't matter how you do it, but just that you could see from the original preconditions, now can you reach the desired post conditions? And that doesn't matter if you have a dexterous hand or you have some parallel jaw gripper, this would be the same. So I'll show you a few examples here. We're spreading. So it's spreading some dressing on a sandwich. And this is the view from a side mounted camera. This is what the robot was seeing, and it starts to fill it up. It's being rewarded during training, and then it learns to put the end effector where it needs to be to succeed. Here it's mashing a banana. And this one it's slicing a celery. And I want to emphasize, the policy that we're training and that visual analysis we're doing is really the same in each of those cases. So certainly this isn't the first real robot to chop a piece of celery, but to think of this characterization of a class of actions that are all about spatially progressing object state changes, this is something new that now we've enabled. And so when we evaluated, we were looking at, I already mentioned kind of the language-based state-of-the-art. Here are a couple of two variants of our approach, whether just using a greedy heuristic based on those masks or using a RL policy at the bottom. And then we did this across the few actions I just showed you: spreading, slicing, mashing, and generalizing across unseen objects. Yeah, Peter.
Does this need any human demonstrations at the first? Like, I mean, if you just said, I want to turn the bread white, like you're doing the reinforcement learning in the real world, and there's no simulation involved there, but you're also doing something from human demonstrations first, right?
In that, the video that trained this segmentation model was people doing these things.
So I guess, yeah, do you need, like, is that overkill? Like, if you just showed a piece of bread without the spread and then one with it, and you just had those, like, you need to actually have people do the task for you in that case?
Yeah, and we didn't, just to be clear, we didn't have people do it. It's just like YouTube videos, right, that train the eventual segmentation model to be able to know. And the premise actually is you want that fine-grained progress. Think of it as like a progress bar. Because if you only have the sparse information about it was blank and now it's full, you don't have that, denser encouragement of how to go in between. And so it really is that kind of growth of the mask, tracking it, that helps this model learn more quickly.
You don't think you could do it like just by, like, if you had the start state and the end state, you could just do like percentage of the way or something like that? Like it's, partly white or.
Well, that's what our model's getting,
I
right?
see.
But whereas the baseline, like this live model, is it knows the end state is, oh, bread totally covered, and it's trying to achieve that goal, but it doesn't have that intermediate progress to hold up against. Yeah.
Sorry for the dumb question, but is that a bagel and olive oil?
I know I had the same question.
Funny.
I think it's supposed to be a donut and syrup.
A donut and syrup.
Yeah.
Okay, and like, like, is this, you're supposed to be spreading it on or dipping it in or like what?
Spreading it on, yeah, spreading it on.
Do you cut the donut in half and then spread it on or?
Yeah, no, that it would be,
What happens if you take syrup and put it on like a glazed donut? Does it
Yeah.
actually just, yeah,
you're
weird.
worried about the actual product of the food, right?
Yeah,
Yeah,
like I'm not sure what the ground truth there is. Like, I don't know what happens when you.
oh, yeah,
syrup-
well, our truth would be, you want it fully covered. And,
Okay.
you know, meaning like from at least the top of the donut, there should be glaze all over it. It's like glazing a donut.
It's like glazing it up. Okay. Sorry.
But yeah, no, this has been a fun project where grocery bills come in for the products we need to use, yeah. Good, but so this is meant to show that versatility because you have this abstraction into these masks, so it allows that versatility. Because it's just saying, no matter the object, this is where it's done, this is where it's not done. Yeah, Eric.
Segmentation conditioned on anything, like for instance, like slicing progress, might be different. If we want something like really finely chopped or like really finely diced, is there like a distinction between that?
Oh, yeah. Yeah, it's such a good question. So this is defined as, what, like we've learned this visual object state changes, actually in cooking, there's differences. Well, you could express like the width of the slice you want or the size of the dice you want. So it'll be expressed that way, like how have we learned what slicing looks like? And we say, and a region's not done until it's the appropriate size. Yeah, so it's always undone until it is that size. Good. Okay, so I wanted to tell you then next about cross-view representations. And here is again where this ego-exo divide is going to come up. And it's very aligned with the challenge of learning and teaching human and robot skills. So with humans, we already said, I'm learning from a coach that I watch from my own perspective, my exo perspective, and I'm seeing myself from my ego perspective. It's a very wide viewpoint change, but we can and we need to translate the actions of someone else onto the actions of ourselves. Similarly with the robot. So the robot sees its own body, sees the world from its perspective, but should watch lots of people and understand how they do things from exo view. And finally, there's this great cog-sci underpinning, in our developmental learning where children, are watching caregivers and from very early age, learning how to map the actions of others onto themselves. So this is a special gap that is important to overcome. And nonetheless, as you probably can see, even from these photos, make a big computer vision challenge because so much looks different, so much is different, even in the visibility of what's there. So we've looked at a few things in this regard that I wanted to share with you. First, we were looking at, okay, imagine I want to have visualizations that go from a teacher's view, what I watch the teacher doing, to imagine how it's going to look for me. And so you can think of this as a viewpoint translation problem where you want to translate from exo view to ego view and anticipate the effects of that, big camera pose change. So can you imagine how it looks through their eyes? And we've trained models to do this. The one here is the diffusion model that we're getting the results in the final right column from our method. Here's a few baselines. Here's the actual ground truth of what, for each of these 1, 2, 3 videos, what it would look like from their perspective. And you can see our prediction on the right, where you're getting some interesting, translation ability, better than what we could do with the existing baselines. And I'm not going into detail on this method, but kind of the heart of it that gave us the power we had was to condition on the detected hand poses, hand object poses in the scene. So in other words, by surfacing what is an important shared detail from ego-exo views, which what are the hands doing, that allowed us to do better generation in this new view. Okay, and this was trained with paired data, right? Because we had all this paired data saying, here's what it looks from both views. Now let's learn how to make that translation. But the next thing I want to show you in a bit more detail is how to think about going beyond paired data for ego-exo learning. Because I hope you can see that it would be really nice if all the time, including when I want to learn a view invariant representation, one that just is effective no matter what viewpoint you give me, if I have paired data across viewpoints, it's straightforward to learn embeddings. You could imagine learning an embedding where you say anytime, these two that were paired, they should be close together, they should be far from the others. We know what to do with that kind of data for view invariant learning. But that kind of data is inherently more limited than any other kind of video data we have that's unpaired. So think internet scale data, which is orders of magnitude greater than paired data, such as ego-exo4D or any others that we have. But we'd like to be able to take piles of exo video, piles of ego video, and still be able to learn from them in a better way for a view invariant representation. So the idea we had is, we nickname it viewpoint Rosetta Stone because we're thinking of this as saying, well, we know how to, separately observe an exo view or separately observe an ego view. If you give us some limited amount of paired data, then we can start to learn, kind of like the translation I just showed you, but learn a transformation between the two. So this limited paired data gives us a paired dictionary from which we could decipher this ego-exo relationship. And the whole beauty or power of the Rosetta Stone, of course, is then you can generalize, right? Because once you know how to move between one or the other, you can start to link in any other unpaired data from one language or the next, or in our case, one viewpoint or the next. So what does this look like? We first train what we call a Rosetta Stone translator. There's a video encoder for ego or exo video, and that'll push it into some latent space. And then we train this with the diffusion process that starts to say, take the ego video on the bottom here and its video clip, and we're going to use this translator to denoise until we get to the associated hallucinated exo latent. So it's a case of ego to exo, but here in the feature space rather than the pixel space. Okay, so you have that ability to then map from one to the other. So then finally, here we go. When we're training the representation, a moment ago I said, well, we would know what to do. You can imagine contrastive learning where we take pairs of video and say, let's keep these close in our learned feature space so that no matter what viewpoint you come from, we understand you as meaning the same thing. But now we can do that with the unpaired data too. So here are some video clips, say, and then for this guy on the top left, someone stirring the flour, we could translate using that translator to some latent space example, which is its pseudo pair. It's the exo counterpart for that ego video. And we do this, across all these samples. And in fact, we go one step further. We do some kind of weighted alignment during training to say we trust most those pseudo pairs that align with language that agrees. So in the event, like we have these language annotations or even pseudo captions, we say if the semantics seem to agree and we've got these pseudo pairs from the viewpoint change, these are strong ones to treat as positive pairs. Okay, so this is how you start to expand from paired data to unpaired data. You kind of unlock the unpaired video, which we have a much greater volume, and train this representation that's view invariant. So before, when we did this, if we were doing retrieval from a video like this is the ego video, and the language is just for our benefit. We're just searching with this video. Then these would be your nearest neighbors under the existing view invariant encoder, one that trained only with the paired data. And at a glance, they look okay, but actually these people are doing different actions. So this isn't a good retrieval. Whereas once you add this viewpoint Rosetta, unlocking that unpaired data, these would be the first 3 retrievals you make. And you'll notice it's able to lock in more on the semantics that align. So this person's getting a cup or a mug, so are all these people. And of course, this matching is happening despite this very wide viewpoint change. Okay, so that's the retrieval task from ego to exo. We're actually doing this across 3 different tasks then in our studies, because think again of that human skill transfer setting where the coach has done it, maybe the coach is in the exo view, like at the top, and now we need to do it. And so we want to be able to have this view invariance between so that even if we train action recognition or even we train proficiency or skill assessment where we score how good is the performance, then we need to be able to test on videos that look like this and 0 shot from ego view. So we've tackled all those tasks. I'm not going through results for all. I take one here just to show you the shape of progress we're able to make. As you add more unpaired data, so back before we couldn't do anything with it. So this was the accuracy we could achieve. So upwards is more accurate. And then, if we did uninformed things with the unpaired data, nothing's going to come of it. But look at how we can start climbing in the accuracy just by unlocking unpaired data, which as things go is kind of a free contribution. Good. And this, by the way, is better than what we could do even if we unlock the data with language, which would be something others would consider in the past. So very promising to open up this data. And I showed kind of how this will allow you to start doing that work kind of agnostic to what viewpoint you're receiving, understand things in a similar way. Now, the other thing I wanted to show you for this ego-exo view reasoning is actually shifting from invariance to informativeness. So what I just showed you said, let's remove all the signals that tell us about the viewpoint so that we can just reason in some common space. Here we're talking about actually caring about preserving the relevance of a viewpoint. And I can illustrate this to you with a how-to video. If you've ever watched one, maybe you've noticed this. Watch what's happening with the camera work. So she's showing you how to do something here. It's taking very, well-selected camera views at every given time moment. Sometimes it's zoomed in on the thing she's making, the tool she's using. Sometimes it's back on her as she says something useful. Sometimes it's back on the whole kitchen as she moves around in the scene. So that's useful for your learning, arguably, right? So you're getting the right informative view when you need it. And we could do this. I mean, it's done today, but expensively, right? Because this is a manual video editing process. Either you've done some camera work or you've recorded all the cameras and now you're orchestrating which one to take at every time point. And so we thought about a new task. What if we could create what we call a varying view video? So it's going to be a single view output, meaning one view at a time comes to your eyes, but we're selecting which one to give. So imagine you had some 3D scene observing something like our bike repair, and then could our job be to say at every time point, which of those cameras should we hop to in order to give the most informative instruction about how to do that task? Okay, and we turned to ego-exo4D in part here. The challenge I'm about to show you that we overcome is that, supervision for such a task of view selection would certainly be niche, is not available at scale. So we had a bit of an insight how to do this from language. So that's what I'm showing you here with ego-exo4D. Like ego4D, if you're familiar, we have language-based narration saying everything about the actions the person's doing. And in particular, these are view agnostic. So they're not conditioned on any one view. And what we did is to train with weak supervision we derive from that language. So no best view labels during training, but we can still learn how to select a view in this way. So suppose that for my training video, the viewpoint agnostic narration is the sentence like this, like the person's inspecting the rear wheel with both hands. So now on our training samples, we'll go against the viewpoints one at a time. So for this viewpoint, we'll do a viewpoint dependent captioning. So automatically caption that segment. Maybe the captioner says the person holds the rear wheel with both hands to inspect it. And now we say, oh, how much does that align with that view agnostic caption? Maybe a lot, 0.9. And we'll do the same for every view, get the view dependent captions compared to the view independent caption. And here's where we derive our pseudo labels. We say a given view for this sample is as good as its independently generated language aligns with the full description of the scene. In other words, the first one was really close. These are a bit lower. So a pseudo label here would say, okay, here's a sample of an action. Here's the views that went with it. This seems to be the best view to reconstruct the meaning of the scene. All right, let me show you what this can do. So yeah, please.
So, do you have a ground truth overall description at inference time as well?
No. Yeah, thanks for mentioning that. So this is only for training. Yeah,
Okay.
at test time, you'll have a video. You'll have K videos that we'll look at here on this thing. Yeah, K views. Yeah, but what the language is doing at training is getting us pseudo labels. So that's kind of our crutch or our, the privileged information, I guess, during training that we won't have at test time, but to give us kind of an indirect path to best view labels. Yeah. So here's an example. You get the multi-views on the left, and you're constructing, this is our output on the right. So this is where we're flipping between cameras based on the content of the video. You can see it zooms out to the full scene, maybe as they're doing some interesting moves or falling from the wall, and then it zoomed to an ego view when they were doing some interesting graphs with their hands. At least that's what we can see in here. And the other example I'll show you, this one's cooking. We have an ego exo on the left, and then our output is on the right. And so again, we're always just choosing which of those two do we want to take, and that's what you see in this big view. And what you tend to notice here is that it'll flip to the ego view as you're doing some object manipulation, like here he's going to start pouring some cereal. And then it'll tend to flip to the exo as they start doing some movement in the scene, like here he's moving back to put it back in the fridge. Okay, and of course, this is what we can read to it, but the whole thing was trained through those auto captions to be able to say, let's maximize the view's alignment with the full semantics of the scene. And that's what you want if you're trying to learn how to do something from a video. You need to see the good stuff that tells you, that reveals the most. Okay, so for time, let me then go to our last bit, where I'm going to briefly talk about some early attempts we've made to go all the way to deploying an AI coach. Okay, and it's going to center around generating language feedback to tell you how to improve. And I really do think this is quite an exciting application direction, where we can think about, human knowledge encapsulated in these millions and millions of how-to videos, themselves very interesting. But what if we have them at scale and together, and an AI that understands them all and can do all this viewpoint, translation and so on? What you can start to do is bring coaching into the hands of a lot more people. So that's what I mean by more accessible AI coaching, because a one-on-one feedback giver is today in person quite expensive. So you're lowering that cost if you have an AI agent that can do that. Furthermore, coverage is an issue. Right now, if you want a coach for XYZ, you better have one wherever you live. And maybe for many people, that just won't be the case, right? Having the expert in the thing they want where they live. But you can change this with this AI-based coaching. And even accessibility in terms of ability, right? And we'll see in a moment how blind and low vision people can really benefit from technology that can transform how-to videos from people into an AI assistant. Okay, so that's my pitch for where our understanding of instructional video is going to change how we learn with an AI coach in ways that really democratizes learning. So it's fun to think about this challenge, and you can say, well, how are you going to start producing an AI coach? What should they even do? And I told you we're going to start with language, commenting on. And so if we had a learner, illustrating a skill like this is someone from EgoXO4D. The question is, what is an actionable advice, or what's an actionable demonstration that we could give her to get better? And you might think, well, let me just show her like what the pinnacle looks like. Here's Steph Curry. This was what you should have done. And I'm joking, right? Because this isn't actionable. That doesn't even count as coaching. If we just say, here's what it should look like, you did that, that's what it should be. And so, instead our hypothesis is to have AI coaches give actionable advice. It certainly needs to be personalized to that video. And in particular, we'd like it to be suggesting how to do things a bit differently than you did, but in other ways, very similar to what you did. So that could be how you're using the body in general, or other facets, but we need something very near to suggest the direction in which you could get better. Is that distinction clear? Okay, so that leads to our approach. And here, let me show you, we hired 50 plus coaches, teachers for EgoXO4D to watch video and give commentary like this.
Great footwork. He's using a dribble to set up his footwork and his shot. Stepping onto that left foot, bringing the ball up. Love that his eyes and head are up. He's already knowing where he's going to go.
Okay, so that was a former college coach, one of our experts, giving that kind of commentary on this video. Of course, we're looking to create AI agents that could be that smart and give that kind of input. So we take videos and commentaries like that from EgoXO4D, and now we take that intuition I just gave you about actionable advice, and we mine for pairs of videos. One like a learner on the left we were looking at, as well as a higher level expert on the right who shares a lot of facets of the video, let's say, except for details that need to be corrected. And that's what's in the language here. It's saying the shooter's using 2 hands, should be using 1, blah, blah. Okay. So mine for videos like that, tuples, where you can say, this is in training, right? You have a learner video, the commentary that they should improve, saying what they should improve, and then a video that shows the improvement, that exact improvement. And now we trained a model, an autoregressive model that I'm not detailing here, but a video language model that now you can give the video as input, and it'll generate that commentary. So this one is saying about that soccer input, our model says the player's stance too straight prevents them from generating the required power and control on the ball. And here we'll look for Peter's feedback if this is adequate advice. So that's a language output, and actually we'll also retrieve a video that shows an illustration of, okay, it's like what you did, but it should be better in the way that you see here. Okay, so that's our personalization. And that's discrete. That's sampling a video we had. We have also started working with some generation, including pose generation, where you could say, no matter what I've seen in the data, here's how your pose should be corrected. And a second final example, the basketball shot on the left from the learner. We say things about bending the knees, generate more power, and then we show how that's going to look like for you. Good, so this is an example, we've evaluated even with human judges, how good is this feedback? But I think an exciting way, starting to bring to life kind of some of the types of techniques we need, including in video language models, to give this feedback. And the final access widening we've done is particularly for blind and low vision users. So you may or may not realize that, even for a blind or low vision user, a how-to video is an asset because it's giving instructions and it has a lot of narration and audio and language. But of course, also limited because right now a person who can't see would listen to the instructions on their phone, or they might call an assistant, call someone to help them to look at what they see through their camera, to give them real-time feedback, which of course requires that kind of availability like we were talking about. And furthermore, how-to videos aren't always, from the default are not geared toward a blind user. So they would say things, oh, you just chop it like this, omitting kind of key physical details, or it'll give you conditions to stop that have to do with how things look, like stop whisking when it's, I guess, when the butter turns brown. So this is a very ripe opportunity to bring in these kind of vision models, which we've done to deploy on some commercial smart glasses to give the user instructions that give the visual details in language that weren't otherwise said, give accessible tips and workarounds, and even give information about that progress so you know when you're done. And I'll show you that with a few of the users here before we close. So here's some proactive info.
Currently mixing the melted butter in the pot. Keep going.
I'm afraid it's a little bit quiet.
Great, you're currently mixing the melted butter in the pot. Keep going.
So it said, you're currently mixing the melted butter in the pot. Keep going. Told her to keep going a couple times, and then it's going to say, okay, great. Looks like it's done now. So that's kind of a proactive coaching. Here's one where it's on request. There's a question she asked.
Hey, assistant, does this look right?
You asked if it looks right. The pancakes in the pan appear to be brown.
Says it appears to be brown. Yeah, looks like it's done. And the last one I'll show you. Here's another question. I hope you can.
Does it look smoky in here?
You asked if it looks smoky in here. No, it does not look smoky.
Cool, thanks.
Okay, you're welcome.
The glasses, she said, does it look smoky in here? No, it doesn't look smoky in here. So you can see these visually grounded questions playing an important role in learning, also safety. And the users who did this system, the blind and low vision users who tested it, could get about 60% less errors in doing these new tasks, which is exciting. And, maybe most importantly, or most exciting to me, it's really fostering that kind of empowerment and accessibility that we were after. So in the studies, from this formal study with these users, here we're quantifying, how helpful was it? How much did it reduce your cognitive load? But let me leave you with two quotes that really say a lot. So one user says, even if sighted volunteers are available 24/7 for free, I want to know that I can achieve it on my own. And secondly, I think it can help blind students get more jobs. A lot of sighted people assume blind people can't learn new skills quickly or follow manuals, but with this we can. And that just says a lot of, the motivation for, no matter the ability, what these kind of one-on-one assistants, advice givers can potentially do for us. All right, so I will close here. I've shared this work summarizing where we're going with skill learning, and be glad to have any further questions.
Thanks, Kristen.
Go ahead.
So you evaluated whether the coaching advice was good. compared to expert advice? Did you do any evaluation of whether they were actually learning from the advice?
Yes. So learning can happen at different time scales, of course. So I think in the vid to coach, the one I just showed, you have the measurements of correctness. So against a control, like how well the skill was executed. I think beyond that, what your question gets at that I think is so important is kind of retention, say. And this, of course, is something that's more challenging to execute, right? For seeing could they do it correctly, and now is their learning happening as in, the next time they do, this skill is better. And really that calls for a couple things. Like one is just the longitudinal data that would allow you to do that. But we also have some ideas of how to bring in even video generation to allow us to start simulating that loop. So it's not just this, oh, coach said this, you did that, or you did that, coach said that, but you did that, coach said that, then you did that. And with video generation, we might be able to start having a parallel kind of simulated evaluation for that.
Cool.
Yes.
For the second work on using language captions for seeing to like decide which view to use, was it like very well correlated with the amount of movement that the head camera was going to? Because I would assume if the head is moving a lot, like across the room, then that would warrant like the exo view instead of the ego view. So
Yeah. Don't think we had that exact baseline, but it sounds like a good one. The related one, what we did do is kind of the other side of that, which is how much can you see the hands, or how much can you see the body? So if we try to maximize, say, the coverage of the body, that was a baseline. That's actually, a reasonable baseline, but it comes behind what we could do once we add the learning. But yeah, it's an interesting one to think about. Just forget the pixels. The movement of the camera might be a signal to use. Yeah, which would be accessible for the model as well. Yeah.
Last question, George.
Yeah. So I was curious about your thoughts when it comes to using 3D information for these skill learning applications. So in some cases you have like more explicit 3D there, like grounding in the 3D world. In other cases it was like the state scenes, the object state scenes project was like maybe 2D masks and 2D segmentation. Just curious what you think. Like, do we need more 3D, or do we like maybe explicit 3D but sparser, so like the location of the objects or the rough body pose of the human? Would you need maybe more detailed 3D, but current systems cannot provide that, so you're bootstrapping on video, or just raw video, like huge amounts of raw video with text should be enough?
Yeah, great menu there. And like, I think that, maybe the safe outcome or answer would be, all the volume of the data and the 3D, like we should certainly be caring of both. I think where we're short on 3D that will make a difference for just even the things I showed, is the detail of the hands. So, we said the fingers right now are not in play, but for these fine-grained manipulations, back to, Adam's point about piano as a great example, we do need that, and need it at temporal, high temporal regularity. So I think that's that. And then the other one, you mentioned the object state change. Yes, I mean, 3D for those would allow us to do, I think, more invariant or more, I don't know, less hands-on control of an action space or the manipulator. But I assume, mashed up avocados are a real pain in the neck for 3D reconstruction.
From what I saw today, I think this was the one that was like would be probably the biggest challenge. Like
Yeah.
State changes like or breaking the egg, and then you have like the going down that.
I think so too. But yeah, that could definitely change things and say getting that from in the wild videos too. Yeah, for the learning.
Okay, thanks, Kristen.
All right, thank you.